Okay, I suggest that we start. So I looked at your comments from last week. So last Wednesday, as a matter of fact, last Monday rather. I looked at your comments from last Monday. Last Wednesday, I left immediately after the class to go to Washington, D.C. for a meeting. So I just put today the survey for the Wednesday class and also for today's class. But I wanted to go back to your comments from last Monday, and there were two things that I paid attention to. Number one, a number of you have complained about your teams. A number of you have complained that many of your teammates have not shown up. And here is what I would suggest. If this is still true a week later, then I think you come and speak with me, because if some of the students are not interested in joining the teams at the end of this class, then they should not impact your performance. So I'm willing to do two things: either move you to a different team or move other people to your team, depending. And it's going to be very critical from this point on that you work with your team to solve the homework problems first, and then also to prepare for the quiz and the final, because this is the team you're going to be working with. The people who are not interested, well, we'll put them all together in one team. I don't know what to say. Obviously, they have to take the final, and then they have to take the quiz. But if for some reason, it's hard to say that they're not interested. I think I should rather say those who have other conflicts that do not permit them to come to this class, then their conflicts should not impact you, all right? So since I've seen those from a number of you, the number was not that big, but even one person is too many if one person is in a team that is dysfunctional. So you come and speak with me. The second topic was the difficulty of the concepts as we moved from the parallel plate waveguide to transmission line. So I have to accept that this material does require a lot of mathematical manipulations, and it's not an easy one. The unfortunate thing is that we don't have too many weeks to complete what I think is at least fundamental for you to go to the next level. So what I will give you today, what you have on Canvas today, is all of the material we are going to cover in this class on transmission lines. And we are going to use this material over and over again. So today, and we'll solve problems tomorrow to solve problems. So I would like to suggest that you come tomorrow, even if it's for 40 people. A lot of times the room is not full. So come to this session. There is no way I can record it, because the room that they have given us does not have recording equipment, and so I cannot do that. But we will solve problems, and I will put the solutions on Canvas. That I can do. The 1 hour we are going to have on Wednesday, we are going to use the same material I'm giving you today to solve more problems. And then we are going to have another problem-solving session before the final. Yes? Yes. Should I bring it closer? Yeah. Thank you. Let's see. How does this do? Should I hold it? Okay. I'll try my best, all right? So in any case, I think my voice projects forward rather. Any case, that's what I wanted to mention. And so today, so we don't, a lot of people said, how should we study for this class? And they are asking for more problems. More problems are not helping unless you find the class too easy. My advice will be first to start with all of the problems that we have solved either on the board, in the homework, or whatever else I have given you, especially the ones we are solving here. The way to study these problems is not to read them and say, I understand what they say, is to read them and then go the next day and try to solve them without looking at the solution. Because until you can solve the problems we solve here without help, then that means you have not understood the material well. So what's the point of going off to more problems if you cannot solve without help the problems we've done in the class? So I would say feel comfortable that you've done all of these problems. In case you have, because of course we have a distribution. Some people have had this material before, maybe a short while ago, others probably a lot longer, much further back. And there may be some people who feel that, all of this that we do, it's so easy that they would like some more. That's the time when I will give you more. But don't ask me for more if you cannot solve what we do. Because for everything that we have, you have the solutions. Because I think if you know how to solve the problems we've done, then you are ready for the final. But in any case, I'm willing to give more problems, but I don't want to give more problems and people who have a problem, who have an issue with what we are doing, try to get into those other problems and get more confused, all right? So that is my philosophy here. But come and speak with me. If for some reason you need some help, please do that. And please come to my office hours as well, as much as you can. All right. So today, very briefly, unless you have any comments, questions, suggestions. Okay. So this is just what you see there. It's just to outline what we have already said, that on the left you have a real circuit. It's a printed circuit board. And you have one input, two outputs. You see those lines we've talked yesterday about finite grounds and so forth. In this particular example, you have lines that look like a microstrip. And last time we talked about limited size of the ground. So obviously, in a real design, the ground does not extend, does not become very big. But in any case, we went, therefore, from a printed circuit board that is much more complex to a transmission line, which is a fundamental component of a printed circuit. And we said the following. We are not going to always deal with a three-dimensional line in space plus time, therefore 4 dimensions. But we are going to use ways to reduce it into something much simpler. And the best we could do is to reduce it to 1 dimension. So what did we do? We eliminated the cross-sectional dimensions, all right? If we have x, y, and z, we took the x and y away, and then we replaced that by a line that had only z, but still had time. And then we went from the time domain to the phasor domain, and we eliminated time. So the line you see here on your right is an ideal transmission line, because that's the only time we represent lines like this. That means that the microstrip we had before, we were able to design it to create a transverse electric magnetic wave, all right? And we said that means that all of the cross-sectional dimensions are much smaller than the wavelength, smaller than 1/10 of a wavelength, each one of them. And then from there, we went to this schematic representation of the line. This line in the phasor domain, to repeat again, has one only dimension, which is along the length of the line. We normally call that z, and has electrical parameters. There are 2 important electrical parameters: characteristic impedance Z0 and gamma, which is called the complex propagation constant. If the line has no losses at all, no losses in the material, and has perfect conductors, that this gamma parameter becomes a imaginary number. So instead of gamma, you have a J beta. We'll see all of this. I'm just summarizing the things that we have seen already. Now, by this, it means that you should feel familiar with this concept, that we have transmission lines that we saw before in statics, at least the first and the last. And then from there, we left that space and we went to ideal transmission lines that are represented by Z naught and gamma, but also by these types of circuits. So a line that is represented by a series resistance and a series inductance, a shunt conductance, and a shunt capacitance. And we said inductance, capacitance, and those resistance or resistances, or one resistance, one conductance, those all are calculated from statics, and both electrostatics and magnetostatics, all right? And therefore, we come down to this line, and we simplify it even further to this form. Because if you have an infinite long line, you take only a very short section of the infinite long line. We call that section delta Z here, so it's small. I spoke about that sometimes. Instead of delta Z, you may say this is my unit length. Whatever your unit length may be, here is delta Z. And for a very short section of the line, you have this very simple equivalent circuit. In the parentheses here, in the frame, you have just information about phasors, how we represent phasors, all right? And then it shows some simple formulas. This is something, if you don't feel comfortable with phasors, take half an hour, and go back to the material you had before and look at that, look at it. And then here it says that if you apply Kirchhoff's laws, the KCL and KVL. KVL is you go around a loop, you sum all of the voltages to 0, all right? KCL is you go to a node and you sum all of the currents to 0. Of course, you have to pay attention which is the direction of from plus to minus for a voltage, and then when a current comes into the node, you may assume it's a plus, but in that case, when it comes out of the node, is a minus, all right? You remember those things about KVL and KCL. Again, we're not going to do any more KVL and KCL here, but this is important to see that from there, we are going to go a little further down and find the characteristic impedance and the propagation constant in terms of R, L, C, and G. Remember that we did last time. It's also here, but we talked about the characteristic impedance and the propagation constant. Also, another thing before we go further is the differentiation between an ideal transmission line that has losses and low losses, we said, because last time I told you that if you are gonna never design a transmission line with high losses. So what's the point to talking about it? So we are talking about a transmission line with low losses. In this case, the characteristic impedance is real, and we'll define the characteristic impedance next. Propagation constant, as I said, is this gamma. So for a transmission line that in a schematic form is like this, you need to remember the following, that one dimension Z equals 0 at the load. And therefore, here it takes negative values. So here, Z will be minus L if L is the length of the line. This line is characterized by characteristic impedance and a propagation constant. So this is an ideal transmission line. Now, if the transmission line is lossless, that means lossless materials if you have more than one lossless material, dielectric, and in fact, let me say dielectric here, and perfect conductors. Okay? In this case, your gamma equals to J beta, and we found that beta last time. Gamma is called the complex propagation constant. Beta is called the propagation constant or the phase constant or sometimes the wave number. And beta, we said, for the lossless case, is 2 pi lambda. All right? Lossy case. Low losses, though, always. What happens in that? You can prove that gamma is a real number plus J beta. Well, this is the attenuation constant. And it's going to be given in, they can give it to you in many different ways, but as a real number over length, because you have to eventually multiply that with Z, all right? We'll see that before. But in any case, attenuation constant here, and this is propagation constant, and this is both are real. All right, so that's what you need to remember, both for the ideal transmission line. Okay? Now, if you go to the RLC circuit, so if you go to this and replace this one by, this is a schematic representation. This is called schematic representation. And this one that I'm going to draw here is called a circuit representation, all right? And it's this one. I will do only for delta Z here instead of the whole. Where R takes care of the losses in the conductor, L is the inductance, G takes care of the losses in the dielectric, and C is the capacitance. And this is for a length delta Z, as you saw before. Okay, if you go to this one, and you apply, and you assume that you excite it here with a source, all right, and then you have here a load, you're going to find that the voltage and the current are related through those equations. We are not going to go in the derivations. If you are interested, you may do it yourself. I'm not going to ask you in any exam to derive it there. But you need to remember that those two equations are derived from here, from the circuit representation. And from those derivations, you can find explicitly in terms of R, L, G, and C, A, and beta. And then, of course, you start from the complex characteristic impedance gamma, and then you find the real part, which is A or alpha. Some people call it alpha, I call it A. And beta, which is the phase constant. So if you have these circuit components here, then you can find Z naught and gamma. Now, we said, though, at that point, that all of this is good for us to understand, because I may give you an R, L, C, and G and say find Z naught and find gamma. Or I may give you Z naught and gamma. And I said the nominal value for Z naught is 50 ohms. So nominal. So practically you will find, and it's in the next, I think, for Z naught. Yes. So you have it on the next slide. But you're going to find for Z naught, this is R plus J omega L and G plus J omega C. However, because the losses are low, always, for low losses, Z naught equals square root of LC. That's it. Always. And then gamma is given by alpha, or A is going to be given by this, and beta is going to be given by that. If there are low losses, obviously, A is going to be non-zero if there are low losses. If there are no losses, then A will be 0, okay? So for this is always that, but for no losses, what do we find? That beta equals, according to this, is going to be the imaginary part of this, which is practically omega square root of LC. Okay? So Z naught and gamma or beta for no losses, are fundamental electrical parameters in the schematic representation. For no losses, we'll have this. And so Z naught and beta, two fundamental electrical parameters for the schematic representation. For the circuit representation, the fundamental parameters are R, L, G, and C. And the others are derivative parameters, all right? So, any questions on this? I'm still summarizing what we have talked about, but it's important to have this summary. All right. Now, we went to the schematic because the moment you know these two, why would you need to go to this one? You don't need it. It's much more complex than that. So the moment you have Z naught and beta, let's assume no losses for now, you are here. And if you are here, I will erase that, you know Z naught and beta. So now that you know, where do you go from there? According to that, and this is a very generic, it's a general solution, all right? So in this particular case, they have incorporated losses. So for the general case, so for no losses, and this is for losses. Let me just so you see both of them. So Z naught and gamma for losses, okay? The same thing here, Z minus L, Z equals 0. All right. In this particular case, so no losses, and here low losses. For this case, and I will write it here, V of Z on the line has two components. We talked about this. V plus of Z and V minus of Z, or you can rewrite them as V naught plus e to the minus gamma Z plus V naught minus e to the gamma Z. And you see that here. And then, of course, I of Z is I plus the same thing, has two contributions. So this is called the voltage wave, the current wave, voltage wave, and current wave. All right? So they both have two components. And they are expressed in similar forms. Okay. This component here is called the incident voltage wave. And this one here is called the reflected voltage wave. And why did we call them like this? Because we said V plus propagates towards the load, and that is because of this negative sign, and V minus comes from the load towards the source. So if you are at the source place, and then you look towards the load, this goes away from you, and this comes towards you. So incident voltage wave, reflected voltage wave. And then the same thing happens to this one. So this is called the incident current wave. And this is called the reflected. And exactly the same thing applies here. The only difference, instead of gamma, you have J beta. All right, so V naught of Z, V of Z here will be V plus of Z plus V minus of Z, and it's going to be V naught plus e to the minus J beta Z plus V naught minus e to the J beta Z. And then for I of Z, the same thing happens. I plus I minus, and that is written like this. Okay? So this is an example where we're not going to do it here. It's all solved in your notes because I'm going to do some other examples. This is a simple one where they give you R, L, and C. And in fact, they give you the two waves. It's a different one. They give you the two waves V of Z and I of Z, and they want you to find the 4 parameters. So you will see how it is solved. It's just plugging into equations. And practically use the expressions of Z naught and gamma naught, excuse me, Z naught and gamma in terms of R, L, G, and C to find the 4 parameters. So I have a question for you. So we have 2 equations for 4 parameters. Why is that possible? We have only 2, we have 4 parameters, unknown, R, okay, R, L, C, and G. And we only have 2 complex equations for V of Z and I of Z. So how is it possible to solve and find 4 unknowns out of 2 equations? Exactly. So they are complex. So the real parts are equal. The imaginary parts are equal. So out of 2 complex equations, you get 4. 4 real equations for 4 real unknowns, okay? And that's how you solve it. Okay. Now, this is for the lossless transmission line. We've talked about this. I repeat. So let's now go to this one. Okay, so with all of this, can I erase this part? We're going to rewrite those equations multiple times. So we're going to try to solve this problem. Try to see, and then in the process of solving this problem, we are going to introduce the reflection coefficient, all right, which we talked a little bit about last time. Let's see. All right. So we have schematic representations from now on only for the lines. So we have this line here. Always make it thick so we don't confuse that for any other wires, because only for the line the length is important. All right? And here I will call this A prime, B prime. And then here at the end we have a load, and it could be complex. So we call it Z sub L. And then here in front we can have a source. In this particular case, the source can have an complex input impedance. And looks like this. Why did I say that can be complex? What does that mean for this load, that it is complex? And I'm in the phasor domain. That if I were to take, if I call this one RL plus JXL, and I wanted to represent it in a circuit form, what kind of a circuit is that? Is? Yes, but and what kind of combination of RLC? Okay, it's going to be either something like that. It can be either something like this, or it can be any resistor in series with any combination of RLC. That's another one. Okay? So you can have any of these as long as the resistor is in series because of this sum. All right, so keep that in mind. Then the same thing applies here. That can be complex. Why is that? Because the source may have storage elements in there. May have inductors, may have capacitors. You know, it's not just that it's going to only have an input impedance, an internal impedance, as it's called. So let's assume that this is V sub S, V sub G, we call it. There I will use the same. Okay, so we said here now that we are going to have the incident V and the reflected V, and of course the incident I and the reflected I. This is a voltage wave. What does that mean? Even if I show it here, does not mean that only applies up on the first wire. The voltage is like this. Okay? And so the incident voltage will go like this. The reflected, as we call the negative, is going to go like this. The incident current is going to go, there are currents on both ones. All right? So, however, you need to remember that I may show them like that, but it does not mean that one happens only on one wire and the other happens on the other wire. No. These two wires are like one entity, okay? So at this point, we define a reflection coefficient gamma, and we call it L because it's at this point. And we define that as the following. In fact, we define it, this is the result of the definition. So we define it as V minus at Z equals 0 over V plus at Z equals 0. Okay? So it's the ratio of the reflected to the incident wave at the load. Since we defined it here like this, I can define it anywhere, at any point Z. And that is going to be my gamma of Z, here I put L because at the load, will be V minus of Z over V plus at Z. So this is a general definition. And then, what do you find? These are important formulas here I'm going to write. I will also write them at the end. So you're going to find that gamma L equals to ZL minus Z naught over ZL plus Z naught, which means that your gamma L will be a complex number. Yes, we have it here. Okay? And then what else do I find about gamma at any position on the line? I can find that at any Z on the line, this reflection coefficient is going to be gamma L e to the minus j2 beta Z. These two are important, both of them. This one gives you the value at L, and this gives you the value everywhere else. Okay. So, the other thing that I would like to do, which it happens here later, but I will do it here anyways, we define gamma L like the ratio between V minus over V plus. Now, we are going to define Z input at any point on the line Z as total V of Z divided by total I of Z. Okay? So how much is this going to be at the load? The load, exactly. So at Z equals 0, Z input at 0 will be the load. Okay? Now, you can prove that Z input at any point Z, so the formulas that I put in squares are important formulas to remember, as also the definition of this one. Okay, Z input then is at any Z, ZL plus J Z naught tangent beta Z divided by Z naught plus J ZL tangent of beta Z. Also important. All right? Now, what else? Characteristic impedance. How do we in the schematic form? We have defined Z naught You remember? We said Z naught is given, like beta, from R, L, G, and C. But Z naught now has some very interesting relationships with these waves. So the interesting relationships is that Z naught is V naught plus over I naught plus, and is minus V naught minus over I naught minus. You can prove that, but I want you to remember this. All of this can be proven, all right, by writing these equations that we had before, the total V and total I in terms of the incident and reflected waves. These are very important. So that's the other equation that is important here. All right. Now, also we said, let's look at some interesting loads. And in fact, I believe, let's start with that. Okay. Any questions about this? Okay. Let me erase this one here. Let's assume that at this point I put what I call here a matched line, matched. Do you see this red from you guys at the back? Okay. Matched line. When do I have that? And let's see, why do I call it matched? Let's assume that the load ZL is equal to Z naught. Let's see what happens. This is the matched line. Here, what happens when ZL equals Z naught? What happens to gamma L? It's very, why so much silence? Zero, zero, zero. Which means nothing is going back, right? Okay, so if gamma is 0 at the end, it's going to be 0 at any point on the line, okay? Let's look at Z in. At ZL, Z in is how much? Z naught. Now, let's look at this one. Let's try to put Z naught wherever is ZL. So I will have Z naught plus J Z naught. And in fact, excuse me, there is going to be, this one, it has a Z naught underneath it. Sometimes you're going to see it here. Let me put it here. Okay, it has an additional. All right, so it's going to be Z naught plus J Z naught tangent beta Z naught plus J Z naught tangent beta Z. So this is numerator and denominator are the same, and therefore that becomes what? Z naught. everywhere, therefore, the characteristic impedance of this line is the load, but everywhere on this line, the input impedance is equal to the characteristic impedance. And that's what happens in the matched case. And what else we found? That the reflection coefficient everywhere is 0. Okay? Now, let us try to look at other cases. Open circuit. So I'll go here. Open circuit load. What does that mean? ZL is how much for an open circuit? Exactly. ZL is infinite large. Okay? All right, now let's go back and recalculate those. We said here it was ZL minus Z naught over ZL plus Z naught. What happens when ZL goes to infinity? Where does this go? 1. So this one here, for an open circuit, gamma sub L becomes 1. And what happens to gamma sub Z is 1 e to the minus j 2 beta Z. Okay? Has a phase. Now, Z in, let's see what happens when ZL goes to infinity. When ZL goes to infinity, that's going to become Z naught. This term is going to be much higher than this term, assuming, of course, that you don't go to a point where the tangent goes to infinity, all right? And this one is going to become much larger than this one, assuming you are not at a place where the tangent goes to 0. So in this case, it's going to become ZL J ZL tangent of beta Z. Okay? So this one goes, and this becomes minus J Z naught cotangent of beta Z, or tangent 1 over inverse of tangent, 1 over tangent. Okay? Now, what does that tell you? When you see that the load has a minus J, what is the nature of the load? It's a capacitance. And of course it makes sense. Why does it make sense that it's a capacitive load? Because if you have a microstrip, all right, let's try to remember the real thing now. If you have a microstrip and terminates at an open end, okay, so this is a conductor, tap conductor. This is the lower conductor. And this is an open end. It stops there. What happens at the end, however? You have two conductors at a distance. And therefore, what is going to happen? There are going to be charges accumulated at the ends. So what is going to happen at the end? You're going to have a capacitance. All right? And therefore, that's why the load in the case of an open end is capacitive at the end, all right? In fact, not at the end. It's capacitive as you come away from it, because it's infinite, of course, and capacitive when you are exactly at z equals 0. But it looks like a capacitive load for as you go close to the end. Okay? It has a minus j. Now, of course, we know also that as we move away from the load, tangent may change its sign. Is that true? Yes. So what means that if we move long enough away from the load, we may see something that looks more like inductive. So the interesting thing on a transmission line that has an open circuit at the end, so open, is that if you are very close or close to enough to the load, you will see something capacitive, but as you move away, it changes to inductive. So the length of the line starts changing the type of impedance that you see as you move away from the line. And let's, in fact, if you want to see how it changes, let's try to see how it's going to change. So let's look at the tangent, first of all. Do you know how the tangent at 0 is 0? How much is the tangent at, say, let's put this here, 0, pi over 2, pi, 3 pi over 2, 2 pi. Okay, let's do that. How much is at tangent at 0 is 0. How much is it pi over 2? Huh? Exactly. It goes like that. And then how does it come back? From here. It goes like this and comes like that. And then it repeats itself. Okay, cotangent, the inverse of that. How does it look? Where is this going to go? This is going to go, when that goes to 0, okay, we're talking about cotangent, 1 over tangent. So it's going to go to infinity, and then okay, and then we use a different color, I guess. Okay, so tangent goes like this. So that tells you that the load, as you move away, so it's all here capacitive until you go and the phase to beta z becomes pi over 2. When it becomes pi over 2, it changes. And then from capacitive becomes inductive. Now here it's negative, but a negative there makes it positive. All right? So then inductive. Then starts capacitive, from infinite goes to infinity. It's capacitive and then inductive. All right? So that is the interesting thing of a transmission line, that as you move along the transmission line, your input impedance changes. So that is for the open end. And then so here we have that gamma L equals 1. So gamma z e to the minus 2 j beta z, and z input minus j z naught. And now you can write it like this or like that. Does not matter. You will see it both ways in the books. Okay? Now, the other interesting one is the opposite of the open circuit, which is what? Short circuit. So I will write it here. Short circuit how much is the load? 0. So if the load is 0, how much is gamma L? Remember, it was ZL minus Z naught, ZL plus Z naught. So how much is gamma L? -1. And gamma Z minus 1 e to the minus j to beta Z. Now, Z input. What is going to happen here? So here, ZL goes to 0, and ZL goes to 0. So this is going to be Z naught J tangent, and of course I need, J tangent, beta Z. So Z input here is J Z naught tangent beta Z, which means that it starts inductive and then it becomes capacitive. Inductive and then capacitive. So again, for a short, that's how you see the impedance changing when you are on this line. All right. Let me see. So all of this is explained there. Okay, it's a summary. What is that? Uh-oh. Well, we have an issue. I think it's time to take a break. And I will figure out exactly why we have a problem here. There. Well, this one is not working. My laptop went to not. Let me see. Yeah, because they had no battery. Need to put it like that. Okay. Yes, tell me.
Can I, for the open circuit load, what does that say for gamma L? Or gamma Z, sorry.
E to the minus 2 j beta Z, or minus j to beta Z.
Minus 2 j beta Z.
Yeah. Let me see. Sure. Okay. Okay.
Unlock the notes online on Canvas.
Let me see. Yeah, okay. Perfect. 1 second.
You like that's fair.
Ah. Okay, tell me, and I will.
For the group homework,
Yes.
there's a question for the first part for B and C to find the incident wave and the reflection
Yes.
wave. Now, is there an actual answer, or is it just the equation that you're...
So you need the equation, and you need to know beta.
Okay.
All right?
And then just
And
plug
as a
that.
matter of fact, I will talk a little bit. Yes, there is an actual answer for this, and I will talk about this now. Okay. So the next thing we're going to do So I would like to solve some problems next. Okay? Let's try to solve some problems. Okay. We are going to talk about the VSWR and the maxima and minima of the voltages on Wednesday, but I would like to solve some problems with what we have now, all right? So this is a transmission line. And usually a lot of times you will see me writing it this way. So we have, in fact, multiple transmission lines. I'll start with the one which is to your right, that section. So we have a transmission line that I give it to you has a characteristic impedance Z naught and a propagation constant B. And then I have another one in fact, they have different lengths, all right? This is L1, and this is L2. And both of them, they have the same Z naught and beta. Now, you could, well, let me go one step back, and instead of showing them as separate, I show them, I'm going to go one step back, all right? So I will show them as one line for now. We have a transmission line. And at the end of it, we have a load. And the front of it, we have a source, whatever. Now, in most cases, when you go to create a circuit, and then you have a transmission line to go and connect to feed a transistor, for example, or one of the gate of the transistor, then in this case, your line is going to have a characteristic impedance, but then at the end, it's going to have a load that is going to be different than Z naught. All right? You don't expect the load to be Z naught. I mean, that's going to be an unexpected coincidence. When you have a line that has like that in circuits, you try to match the line. So how do we match the line? You remember, when is a line matched? Yes, if at some point on, from some point on, the input impedance of this line is Z naught. If at any point we can make Z naught equal, Z input equal to Z naught, from any other point on here, it's going to be matched. All right? So the goal when we design interconnects is not only to know Z naught and beta, but also to eliminate reflections. And when do we eliminate reflections? When they are matched. So eliminate reflections. Reflections are totally unwanted. Why is that? Because you want to send as much power to your load through the transmission line or the interconnect. And if you have reflection, that means part of the power you try to send the load is going to come back to you. But you don't have infinite power. A lot of times power is extremely expensive in circuits. So you have to eliminate every reflection. How do you eliminate reflections? You have to come at some point here, and that's part of a design. So we're not going to design here, but we're going to do the analysis piece. But through a design, I have to place somewhere on the line a load, complex load, at some point. So I have to break the line, and then at some point of this line, place another load so that the reflection here, and usually I show the reflection coefficient like that, at this point, whatever, I can call it here Z sub m, is 0. If I can make, and then so I don't know how much this is, and I don't know this distance. But if I could find a distance, and if I could find a load, so that my reflection coefficient here was 0, then practically I could match this line. This is the whole concept. And everything you do here, this piece of the circuit, including the section of the line here and the load, is called the matching network or matching circuit. So here is called matching circuit. Okay? Now, to be able to even do the design, you have to know how to do the analysis. So now, in this particular problem, I'm giving you everything, all right? So instead of asking for these two, the design problem is more difficult, as you can imagine, than the analysis. In this particular, therefore, analysis problem, just as an example, we give you everything. I give you everything. What I give you is that this length here is a quarter of a wavelength. And I also give you that this length here is the same thing. I only give you lengths for the lines, the transmission lines, and not for the wires that I put in between. And then I also give you that this is Z sub S, and I call it Z sub S for stub, because anything that we put on a line like this, we are not going to go and stick a resistor in a microstrip, all right? You cannot do that. But you're going to put a section of a line. And we will talk about this next time. But for now, it's a load, Z sub S. So what do I give you here? I give you Z naught is 50 ohms. I give you Z sub L to be 200 plus J50 ohms. And I give you Z sub S to be minus J250. So what is Z sub S? What kind of a load do I put there? A shunt capacitor. That's what I place there. Okay. Now, rule number 1. We work with rules here. First of all, we know that we are going to always use this formula along the line. Excuse me. In. Okay? We always know that. So what we have to do to be able to find Z in, so I will have to find Z in here, which I know, obviously, all right? So I will need to find Z in here. And then find it here. And then I will have to move it by another length and find it here. All right? So the first thing, since this formula, I have this formula that tells me if I were to work from this towards the load, then if I knew how much is the total Z input here, then I can use this formula, where my Z input would be the new load. All right? So if I start working from here, and as a matter of fact, usually the best way to develop that, all right, you will see, we'll come to this. The best, I will call it A and A prime, just because we know this point. All right, and this is my load. Okay, so practically I have to find, so I need to find Z in at A prime. Yes?
What is a shunt load?
A shunt load is one that goes in parallel.
Okay, so it's just a parallel load instead of just a single load at the end.
Yes. So we call them shunt and series loads for this kind of circuit design. Okay. It's a configuration. All right. So Z, I need to find Z in here. To find Z in there, what do I need to know? I need to know this, which I do, and what else do I need to know? I need to know this input impedance here. All right? I need to know this one. And this is Z in. And I call that Z in only. So I need to find the input impedance before this shunt load. If I know that, then I will have one impedance in parallel with the other, and then I can move it forward. Now, there is another rule. So this is the thinking. This is the thinking no matter what loads you have. That as you transfer, as you want to find in a complex load the impedance here, you start working your way here, this way. So I have to come from here, there first. Find this one. Then I have to come here, find this one. And then I have to come here. All right? The reason I made these steps is because I thought, what do I need to find the impedance here? That's how I defined what I need to calculate. There is another rule that you need to keep in mind. And the rule is the following. If I have only shunt loads, like here, you can consider it to be a shunt even if it's at the end. Definitely this is a shunt load, and this is input impedance. A lot of times, to simplify things, because in shunt configurations, if you have resistive loads, you don't sum them up, all right? It's like a in parallel combination of resistors. When you have shunt loads, you transfer everything to an admittance. But we are not going to do this now. I will do this later. For now, I will keep it the way it is with the impedances, even if in the expressions that I have there, you will see in how we solved it much simpler. But here we'll go brute force. We'll do the difficult thing, but the one that is most obvious. Okay, ZL, I gave it, is a complex. One thing that I can do that is going to save me a lot of calculations will be to normalize everything here with respect to Z0. So I normalize, and that's because it saves me calculations. I normalize all impedances with respect to Z0. You can do that, of course, if you have the same Z0 everywhere. All right? So if I what does it mean normalize? Z in normalized is nothing else but Z in divided by Z0. ZL normalized is nothing else but ZL divided by Z0. All right? And if you do these things ahead of time, that simplifies. How does it simplify? then Z in is nothing else but ZL, the bar above means normalized, plus J tangent beta Z, and then we have 1 plus J ZL normalized tangent beta Z. If you do these calculations ahead of time and you come here, you will have fewer calculations to make. So that's the reason we normalize things. Any questions so far? So far, I'm still developing. It's like cooking. I'm not trying to make the food yet. I put all the ingredients, all right, around. And then you make sure that you have enough quantities and everything. That's what I'm doing here. I'm still preparing everything the way it will help me find the final solution. All right, so do you remember what I said? I need to find, first of all, Z in here. We have that. Z in there, normalized. Let me normalize it. How much is Z in here at the load? Is ZEL divided by Z naught. 50, so it's going to be 4 plus J. Okay? And of course, it's just a number. It does not have units. All right, forget about the inverse there that I do. Let's follow what I'm doing here on the board. Now, this is where we are. I have to move by how much? A quarter of a wavelength, all right? How much, therefore, what do I have to do? I have to calculate, this was Z. Let's put that Z. I have to calculate Z, beta Z, I should say. Beta Z is how much? 2 pi over lambda times lambda over 4. Okay? 2 pi over 2. How much is the tangent of pi over 2? Which means what? Well, Z in equals 1 over ZL, normalized. So this is very important. What does that say? When you move along your line by a quarter of a wavelength, you invert your input impedance is the inverse of the load. So you don't even have to calculate that. So all of these are important to save calculations. So you need to remember that when I move along the line by a quarter of a wavelength, I invert the load. The impedance practically is the inverse of the load. Normalized. Let me ask you this. What would happen if the length was half a wavelength? So if I invert it again, what happens? Becomes the same. If my distance were to be half a wavelength, my input impedance tangent beta Z would have been 0, and my input impedance would have been the load. So practically every time I move on the line by half a wavelength, I see the same load. All right, so I'm going to write these two things because they're important. So what have we found so far? So in a line that has a line Z naught beta, when the length D or L is pi over 4, then normalized Z in is 1 over normalized ZL. When the length of the line is pi over 2, then Z in is ZL. And that repeats. So 3 pi over 4 is going to be that. Pi is going to be this, and so forth. Continuous, all right? Because its phase goes in a circle. This is very important to remember, because now this one, I know I just invert my ZL, and there this one, so Z in prime at this point, not prime, at this point is 0.8 minus J 0.2. You just find the inverse of a complex number. All right. After that, what do I need to do to find the rest? How do I find Z input prime? What do I have to do to get this in parallel with that? Yeah, so I have ZS in parallel. That's how I saw it, all right, schematically. Which is how much? ZS, Z in AA prime divided by ZS plus Z in AA prime, correct? Okay. So how much is my Z in AA prime is 1 over ZL. So this one is going to give me ZS divided by ZL, ZS plus 1 over ZL, which in fact is going to give me ZS 1 plus ZS times ZL, normalized. And as a matter of fact, I have to be able to connect the normalized quantities with ZS. I have to normalize that too. So up to here is correct, but here, this would need to be normalized, okay, to be able to make those calculations. So it's correct up to here. But if I want to do normalized quantities, they all have to be normalized. So I have to go back and normalize here, okay? This is ZS, and then becomes this simple entity. And then what do I do next? I move another quarter of a wavelength. So how much is my total input impedance here? The invert of this, which is 1 plus ZS, ZL divided by ZS. And that's how you find the input impedance at in the beginning of this line. Any questions? Yes.
What's that notation with the slash AA prime? Are you just saying at the point AA prime?
Yes. That's how you saw it. And it's important, you know, when you solve problems like this, to name your nodes. Usually I would name in what I give you all of the nodes, so you don't get confused because there are so many points on the line. You need to make sure you don't confuse at what point on the line you are computing something. So every time you have here practically, ideally I would put here B. You will see probably in the homework. And I could put C here, C prime. So whenever we talk about it, and then I denote it like that, I know where I am. But you need, where you have a load, you need to be careful whether you are before it or after it. All right, in your calculations. Any questions on this? Of course, what I have in my notes is another thing. So I said, okay, and in fact, the result will be the same. I would say, you know what? I don't want to add here parallel loads. I don't want to find the result of parallel impedances. So I can take everything and place them in admittances. if I do that, you find something very interesting. So before I erase that, I will just very briefly, I would like you to remember this on how to solve the problem using impedances. And then you go to my notes and see how I solved it also using admittances. And what is the difference between a solution in impedances and admittances? Not much, it's just maybe a little easier to make calculations along the line. So here I would erase that. And I will write another equation for you here. So if we have an expression for the impedance, can we find an expression for the admittance? Yes. And how would we do that? We take the inverse in each one of those. So it's going to be 1 over yn equals 1 over y naught. Of course, characteristic admittance is the inverse of characteristic impedance. Okay? And if you like, I will write it here. I mean, erase so you don't get confused with all of this. So this would be inverse of that, inverse of this, I don't do anything with the tangents, inverse of this, inverse of this, okay. Now I invert, and as a matter of fact, here I will get rid of this. In fact, sorry about that. It should be y naught. I will multiply with this so I can get rid of them. And in fact, I will also invert this one. So it's going to be y in, y naught from here. And here it's going to be yl plus j y naught tangent of beta z. And here is going to be y naught plus j yl tangent of beta z. What does that tell you? That and then of course normalized. And here I will have to show you that this one is 1 over z naught. This one is 1 over z in. This one is 1 over zl. And also this applies, all right? I can normalize them too. So that says that the normalized admittance, when you normalize admittances, you normalize them with respect to the characteristic admittance, will be normalized yl plus j tangent beta z, and normalized n1 plus j normalized yl tangent beta z. So the formula is the same with the characteristic, with, excuse me, the normalized impedances, but everything has to be an admittance here. All right, so the formula for input admittance and input impedance are identical as long as all of the impedances have been replaced by their own admittances. Okay? You have the same formula. So if I have something that looks like this, and I anticipate to find something that is going to come here is going to be in parallel, I said, okay, why do I not change my problem in admittances only? Let's assume that this is my YL. It's the inverse of, this is going to be my Y naught. This is going to be Y sub S, okay, Y naught. And this is going to be Y. All right. So what, and this will be all y's. Y. Okay, what happens if I move here by a quarter of a wavelength? What happens to the admittance, the input admittance? Inverse. So at this point, Y in, and I normalize in my expressions, will be 1 over YL. Okay? How much is here my input impedance? Admittance is going to be the sum of the two because now I'm in parallel. So it's going to be YS plus this one, which is 1 over YL. Okay? And how much then am I going to move this here? The inverse of that, which in fact here I can make it 1 plus YL YS divided by YL. So how much is my input admittance here? It's going to be the inverse of this. So it's YL 1 plus YL YS. So I've been able to solve it also the same problem with admittances. Any questions so far?
Why did you invert it with me?
Because of lambda over 4. Okay. Okay. Now, let me see. We have a little bit of time, and I have some very simple, nothing on this, but simple, some top hat. We'll solve more problems like this tomorrow. Okay. Let me see. Terminated line. Okay. It says here that a lossless transmission line is terminated in a purely resistive load. The load voltage reflection coefficient of the line is gamma L. And for this case, it asks you to find which of the two is correct, which of the following so many options. So it asks you to find the reflection coefficient at the load, which of all of these that may be. And so, but I give you something, they say I give you specifically the characteristic impedance and the load, all right? Do not miss that. So I will assign it, and then I will remove it from here. So you will have 5 minutes to solve that. All right, read my specifications too for this problem. You cannot see it? What? So you see it, okay. Yeah. Yes.
When you say that the impedance of the line is 50 ohms, is that real, imaginary, the magnitude?
Z naught is always real, no matter what, okay? Okay, so you guys try to finish it in a minute. 1 minute. Is there anybody who has not entered yet? I want to make sure I don't unassign it while people are still working. Okay, I will unassign it. Is that okay? And let's see. And let me show Okay. So those few who put B, ZL, how much was the load? 200. Okay, let me erase some parts here. Okay. The load was 200. And Z naught was 50. How much is gamma at the load? Positive. Okay? One more and we're gone. It's easy. What's that? You guys want to leave? Yes. Okay, listen. I'm going to let the next one on, but you're going to promise to me you're going to work on this until later tonight. Yes? Okay, good. All right, you're good.
I don't know how does this change to negative over here in the positive.
Yes, because, so what is this? Let me see the formula. Sorry. Z naught.
You factor out the Z naught and then it suddenly become negative. I don't know.
So, well, let me see.
Or do I copy it wrong?
There is, no, you have not copied wrong. So this is ZL, isn't it?
Yeah, ZL.
Yeah, okay, perfect. So the ZL is VL over IL, all right? V at 0 over I at 0, which is V naught plus V naught minus, I naught plus I naught minus. But we know that V naught plus over I naught plus equals Z naught, which is minus V naught minus over I naught minus. It's because of that.
So you factor out. Oh, okay.
Yeah,
okay.
see?
Oh, got it.
Yeah.
And also for the
About the groups.
for wait, one more question. So for like when we're finding the B naught plus, we use this equation.
Yes.
And then we're finding B naught minus, we just multiply by gamma, right?
Yes.
I guess that's it.
Okay.
Yeah.
Okay. Sure. All right. Tell me, what are your